Hey everyone, so today is March the 23rd and it's our first online class for the 765 due to the coronavirus. Welcome to the class and I'm glad to see you back after the long spring break. In the following, I'm gonna stop my video and share my screen. Okay, I assume that everybody can see my screen, right? Can everybody see like my screen sharing? First is a Word document, the other thing is the class notes. Everybody can see, right? Just note your door if note your head, sorry, if you everybody can see it. Can you guys see it? The slides here? Okay, very good. Okay, so in this class we're gonna introduce let me be a bit bigger. In this class, we're going to introduce LDA. The total name is Linear Discriminant Analysis. As I recall, we just finished, let me see, lecture 6, which is, let me open it, which is the logistic regression, okay? And you're going to see LDA and the logistic regression, they're very, very similar. First of all, just recall the logistic regression. You're going to do like this way. You're going to take the log ratio and the right-hand side is a linear model. And by this way, you know, we do the steps and finally we can calculate the posterior. And later what we do is that we analyze the case for two classes. In other words, m equals to 2, and we assume a multi-Rounding distribution for y, the label space. And of course, if m equals to 2, meaning that we have only two classes, then the multi-Nowley becomes the Bernoulli distribution. And you know, by the MLE, we get this. And then finally, you know, we use Newton's method and IRLS method. Again, I cannot remember the full name of IRLS. Iterative, let me see. IRLS, I remember iterative. Where it is? Iteratively related least squares. And we can get this one. And finally, I remember I showed the example. This is from Tipshirani's book. And we can get the result. Then let's have a look at the discriminant analysis. First, what does discriminant mean? In English, discriminant means something very different. It's going to be distinguished from, you know, some things going to be very different from others. This is meaning of discriminant. And the discriminant analysis, the point is here. Give me 1 second. Let me use annotate here. Oops, I'm also learning how to use the Zoom online. Okay, let me put my spotlight so that you can see my mouse very clearly. But here I do want to write a box. This is very important. The discriminant analysis is to model the difference between the classes of the data. So suppose I have, say, m classes. I'm going to do something like 1 to all or 1 to 1, this kind of pairs. I'm going to compare. Before formally introducing it, we're going to first spend the posterior by what? By our Bayesian, the Bayes formula, okay? And we're going to write in this way here. So here, let me clear all joins. I wish I have an eraser, which is going to be easier and faster. So here, my f is what? The f is the conditional density probability of x given class k, which is the likelihood. And the pi k is nothing but a prior distribution, okay? I suppose we know. Suppose that we know fk, we know pi k. Later, you're going to see it's super easy to be estimated using the same way as we did in the naive Bayes. And then, of course, since pi k is a prior distribution, we must have sigma of pi k equal to 1, okay? Now let's have a look at, oops, I click this and come here. Okay, here we go. So now let's have a look. What does LDA mean? LDA means linear discriminant analysis. Okay. For the traditional LDA, we usually have two assumptions. Assumptions number one is that given class C equals to K, meaning that we're in class K, then the data X is assumed to be normally distributed. Of course, here's a multivariate normal distribution with the mean as a vector, with a mu K as the mean and a sigma K as the covariance matrix, okay? So this is a PDF. what is PDF? Probability density function of the what? Of the multivariate normal distribution. And the second assumption is that we assume all sigma k's are the same. In other words, all variables have the same covariance matrix. So I don't need to have a k here. Now, again, the discriminant analysis is to, let's see, is to model the difference between the classes. To achieve this, so what is the difference between different classes, right? What we're gonna do is that we're gonna do it in this way. For example, I'm comparing the log ratio of class K versus class L. You can see it. And remember, this is the same as what? The technique that we used in the in the logistic regression. Remember it? Okay, now let's have a look. Suppose my Fk is in this way. Okay, then after calculation, what we're gonna have. So this is very simple. You can easily see it because this PCK given x equal to x, it's here. I think it's better for me to still draw it. Let me see. Okay, let me draw a box. I'm gonna use this one, and from here I can have this. Do I have arrow? Yes, I do have. I have this. Okay, so you just substitute. Very simple. Why? Because see the denominator. The denominator is a common thing. For any L or K, this denominator will be canceled because I have the log ratio. So you only have actually the numerator, and because you're comparing the class of probability, actually the posterior probability of class C versus class L. So you're gonna do nothing but this times this of K over FL x times pi L. And since it's a log, you can easily decompose it in this way. Okay, this is very simple. The next step is that, well, because I have assumption that they are Gaussian distributed with the same sigma. Oops, how do we delete it? Undo. Okay, let me see. Go back to the box with the same sigma. Okay, excuse me. So that I can just write it in this way, because the log f by f, everybody can see it. This item cancel. Again, here we have the same sigma. This item cancel. So it's gonna be nothing. And also e and the log are canceled. It's gonna be nothing but just this part, this exponential part. Okay, and you're gonna use this one of k minus this one of L, and you're gonna have this. Okay, minus k. This is just this. Let me see. I hate that I don't have a pen here. Okay, this is just this. Okay, and also this is this. Because why? Because both of them, this part is from here. And the second part, we just copy and paste, doing nothing. Clear? Any questions here? This is very simple. I wish I have a whiteboard so I can easily write it. But here I only have a word. It's kind of typing it is kind of slow. This part is not that difficult. I think it's easy to understand. Get a point, everybody? Okay, very good. Now let's continue. Then the thing is, how do I go here? Because clearly I can have some further, I should be able to have some further simplification here, right? Why? Because let's say use the most stupid way. You just expand it one by one. So 4 items, actually 3 items. Why? Because xt sigma inverse of mu k equals to mu kt of sigma inverse x. This is just a coefficient of 2, right? So you can clearly see first xt sigma inverse here x, and here I have a minus, so they can be canceled, right? And some items can be combined. So here I use the trick. The trick is like this way. Let me how to. Let me see, spot. Oops. How to, let me see. Okay, good. The trick is in this way. So I'm pretty sure everybody, okay, let's clear. I cannot tolerate it. The trick is this. Everybody knows that, let me make it bigger, 13, let's say. A minus B square times, oops. A minus B square times, let's say, C minus D square, not times, minus. Everybody knows how to calculate it, right? This equals, oh, no, I'm so stupid. Let me directly do this. A squared minus B squared. Make my life easier. So this equal to what? This simply equals to A plus B times A minus B. Right? Super simple, right? Okay, the same. Have a look at here. This item here, kind of like a square. Why? Because this is T times something, and this is not T. You know, the vector itself. You know what I mean? In the sense of a square. So this is exactly the same as this form, like A squared minus B squared. So what do you need to do as simply like this? Where's my draw here? You're gonna use this one minus this one. I think the first item I put here is plus. It doesn't matter minus or plus before. You're going to use this item to plus this item, so that you're going to have x minus mu k plus x minus ul, and keep this sigma inverse here, because that's a common part. Both of them have this sigma inverse here, okay? And the last part is this item minus this item, okay? So you're going to have x minus mu k minus x plus mu l. And of course, the last item about the prior distribution, you're going to keep it. And then see here, it's super simple. Cancel, cancel, see it? And this item becomes what? 2x minus mu k minus mu l t, and you have this. And from here, it's, you know, of course, very, very simple. You just do some super simple, you know, this kind of calculations. And you're gonna have what? And you're gonna have the final equation here, 3e. Any questions regarding the steps here? This is basically, you know, some matrix games. You are strongly recommended after the class to calculate step by step by yourself. Okay, I don't think it's going to be really difficult for you guys. Okay, and hence from this equation, what can you see? Something interesting. Have a look at here. For a given x, this is what? This is linear. See it? Because inverse of sigma times mu k minus mu l, this is a parameter, like a coefficient of x. Okay. And have a look at the second part. This is what? There's no x here. So the total equation of 3e is what? Is a linear function with respect to x. See it? It is actually the same as this. Let me again. Let me. How to go back? Okay, here I can go. 3e is equivalent to the following. Let's say I can say WT, WT, I do need a bold W, X plus, let's say, W0. You know what I mean? This X is this X, and the WT is actually this item. Oops, why cannot select it? Anyway, it's this item. Oh no, it doesn't let me select it. Inverse of sigma times mu k minus mu l, okay? And the whole, this item is nothing but W0, okay? It's simple. Okay, and since, oh my God, again, I have to clear. Since it's a linear function, and you know what is the decision boundary? Decision boundary simply means this one equal to 0. 3e equal to 0 gives you what? Gives you actually a hyperplane. See it? You know what I mean? For example, you can just have a look at here. What is this? Let me write it as this way. The good point is that I can copy and paste. While in the whiteboard, I cannot do it. On the decision boundary, we have this equal to 0. Which gives a hyperplane with respect to x.
I have a question.
Yes.
Why we put 3e equal to 0?
Because I want to see the decision boundary. Why? Because what does decision boundary mean? This is something here. Can I ask you a question after introducing this part? Give me about 2 minutes. I'm gonna finish it. Okay. So okay. Any other questions? Give me about 2 minutes. You're gonna see why. Any other questions? No. Okay. Now let's have a look at here, which is very, very related with Said's question. So how do we make a prediction? Suppose I give you a test data X. What you're gonna do is that, okay, and suppose I have all these parameters. Suppose I know, let's say mu and a sigma or something, everything I know, okay? What I'm gonna do is that I'm gonna, excuse me, I'm gonna define a linear discriminant function in this way. And I'm gonna see which one has the biggest probability, right? Because basically, remember, suppose I know all the posterior distribution. How would you make the decision? You're gonna predict it as the biggest, the class with the biggest probability, right? Which is actually a Bayesian view, right? Okay, so this is equivalent to what? Equivalent to this. I'm gonna predict by the argmax of Cx, where Cx is the linear discriminant function defined in this way. Why? Because if you compare phi with 3e, you see what I mean? It's something, a comparison of Cck minus Cl. See it?
Yeah, Dr. Shu?
Yes.
I think there is some network problem here. Your voice is not clear, actually.
Oops. Hello, can you hear me?
I can hear you clearly.
Network. Maybe my home network is not too good. I don't know. How much you pay for the network? Anyway, I forgot we're on recording. Anyway, let's go back to the topic.
Now clear.
Okay. So let me repeat it again. So here I'm gonna make the decision that I have. I'm gonna make a decision based on what? Based on the biggest probability, right? This is what we did for almost all these lectures, right? So that suppose, for example, I know all the probability Ck, k from 1 to n, then for a given data x, which label would you predict? You're gonna find the maximum probability, and then you're gonna predict the label to that one, right? Okay, yep. Which is the Bayesian view. Now the thing is, how can we do it through 3e? A simple way is because here I have the log. See, a log probability divided by another probability under log, okay? So that I just need to define this C, which is called a linear discriminant function in this way. And this is the phi is from where? It's from 3e. If you observe 3 and 5, you see what is the difference? The difference is that 3e equals Ckx minus Klx. See it? Right? Very, I cannot say really equal. The reason because this item, it's not really equal, but the difference is just a constant. You know, it doesn't matter when we're doing argmax, who cares? A constant. Okay. So, and of course here, here is satisfied. Be careful, okay? This one, and if you make this one minus a k, you will have some items, okay? Not directly equal to this one. Be careful. Okay, then we can go back to Said, your question. You asked why we want to make them equal to 0, right? Okay. Have a look at Said, this side. Suppose Ck of the probability equals to this probability when C equal to L. What the value it should be? You're going to have log 1, right? Suppose these two probabilities are equal.
Exactly. Log 1 is
so
0.
that you have what? This one equal to 0. See it? And that is the decision boundary. Because if the class K and the class L are equal, you don't know which one really to choose. I remember I have a figure here. It's somewhere here. Let me see. Here you go. You are gonna exactly on this red line. It's the decision boundary. It doesn't matter you choose class 1 or class 2. They're the same, right?
Okay.
And in this case, you see what? I see here. This one equal to 0, right? Which is here. See it? That's the reason why I want to have a look at this one equal to 0. And from this item, you see what? What is a set of x? Any point that satisfy W, the set of them will what? Give you a hyperplane, see it, with respect to x. Okay, that's the reason why we claim that the decision boundary here is a hyperplane. And that's linear, of course. And that's also the reason why it's called a linear discriminant analysis. Okay, because this item's linear here. Okay. Now we have known, let's say, the probable, have known how to make the decision. And again, this decision is nothing but a Bayesian optimal decision rule, you know. And we have had the logistic. Hello? It showed my internet connection is unstable. Can you hear me?
I can hear you. It doesn't have any problem.
Interesting. I don't know.
Yeah.
Anyway, if you cannot hear me, just let me know. And by the way, feel free to unmute yourself, okay? And then that means as long as I know all these number, all these mu k, mu l, all these parameters, and also sigma, where's sigma here, then I can make a prediction. The problem is that in the real cases, you never know what are these, right? However, remember, in the traditional LDA, we do have two assumptions. First, all of these are what? Normally distributed. And the second thing is that all sigmas are the same. So immediately, I can use this way to estimate. Let me draw a box here. I can use this way to estimate these parameters. We have three groups of the parameters. First, the prior distribution of k, class k. Second, the mu k, which is the mean vector for what? The mean vector for x when class is equal to k. And the third is the common covariance matrix. Okay. Do you have any questions about the m here? Why there's an m? Remember, usually we have n minus 1 rather than n minus m. But why here I have an m? The reason is because I'm considering m different classes. So for the sake of degrees of freedom, I'm going to make them balanced. So I'm going to have n minus m rather than n minus 1. By contrast, usually you consider only two cases, in or not in. That's why you're going to have n minus 1. Okay. Of course, some people would use n minus m minus 1. It doesn't matter. It's not a big deal. It's something like the estimated population variance versus the sample variance. It's something like this way. The main reason we can estimate in this way directly is because of the assumption that x, that is here. Again, I have to clear it. That's something I really dislike. Okay, it's because of this. I have the assumption that x is normally distributed, so that I can easily use that way to estimate it from the normal probability theory. You know. Okay, and here gives you an example. Let me make it bigger. Here gives you an example. Consider the data. Okay, 1, 2, 3 meaning there are 1, 2, 3, 3 classes, and you can see what. Oops, you can see this is the boundary for the LDA, and well, the result is not too bad, which is also not too good. Okay, oops. Is there a way I can make it to? How to? I have some technical problem here. Okay, let's use this. Here's easier. Yes, here at least I can drag. Okay. Any questions so far about the LDA, traditional LDA so far? Actually, it's pretty basic. Okay. From the definition.
Well, I have a question here.
Yes. Yes.
So based on the data set that we have, I mean the testing one. So we have the hyperplane equation, and then how we make a decision.
Yes, you make a decision like this way. First, you're gonna estimate the pi k, mu k, and the sigma, right? Now suppose I've already known this, right? And then I'm gonna do this. I'm gonna predict the target, the label of the target data to the argmax of Ck, where Ck is the linear discriminant function generated from here, from the log ratio here. Whichever is the maximum, I'm gonna predict the label to be that one. Done.
Okay.
And guys, think about this. In the logistic regression, I think I do have a lecture 6 here. Okay, oops, smaller. Let's compare. What did we do for the logistic regression? And that's gonna. Why it's so ugly here? What happened here? Cannot. Yeah. Okay, I click tool must. In the logistic regression, what did we do? We did it like this way. So first, we have a model here, and we have a model for a probabilistic model, which is a Bernoulli distribution for the y. See it? And all the stories after it is based on this, including our MLE, including our Newton's method, and later we use the IRLS method, right? But here, look, we don't have anything about a multi-Bernoulli distribution. We're just simply doing this way. See it? And you can clearly see this is much simpler, much simpler, because this is everything you can do. Very easy, right? Okay, and there's another thing I want to ask is, do you know why here we cannot simply use this way, but here we can simply use this way? Actually, I just mentioned the reasons again, because we have assumption that all axes, given the class K, all axes follows normal distribution. Okay, this is just very simple normal distribution theories, that if the xi's are normal, so their mu can be estimated as the average of the sample, which is an unbiased estimator, remember it? And the same for the sigma. Okay, now let's continue. So what if I have only 2 classes instead of K classes? Similar here in the logistic regression, we also emphasize on the 2 classes, right? Because in practical cases, 2 classes are the most common cases. Let's have a look. Because we have this one here. We have this one here. Where? We have this one here. So anyway, let me do one thing. Sorry guys, please wait me for several seconds. Let me copy and paste this one so that I can use a double screen to see it. Otherwise, it's gonna be kind of like a chaos. Let me put that 1 for example. Okay, now I can open 2 lecture 7s. Otherwise, kind of like switch again, really confuse me. Okay, and this lecture 7 would be here. Okay, both of them are lecture 7 now. Okay, so so here I can show you the page here, and here I can show something I need to refer to. So from here, if I have 2 classes, in other words, for example, here k equals to 2 and L equal to 1, you're gonna make the decision what? If and only if this one is greater than or equal to 0, right? Why? Because log 1 equals to 0. If this one is greater than or equal to 0, that means what? Let's say strictly greater than 0. That means your PC equals to 2, k equals to 2, okay? Is greater than PC equal to 1. That means I'm gonna predict the label to be class 2, right? That's why we will predict its label to class 2 if 3e is greater than or equal to greater than 0. In other words, you have this. And of course, you can calculate these parameters as I wrote here by the equations given in 6 here. So this is very simple. I just need to calculate it 1 time and I immediately know my decision, right? Again, by comparison with the logistic regression, I don't have a here actually Bernoulli distribution, and I don't need to have any very difficult or complicated calculations. Okay. Then the problem is what? The problem is that we estimate using this way. It's kind of, people may feel it's kind of unsafe. Do you know why people may feel unsafe? Or let's say, let me ask you in this way. Do you have any questions if I just simply estimate in this way? First of all, statistically, it's of course correct, because again, they're normally distributed. But the problem is that compare with the logic model, with the logistic regression here, what did you see? Where's the logistic regression? It's here. So here is the modeling part of the logistic regression. The key difference is that here I use the multi-Raouli distribution, and of course, if I have a Bernoulli if I have 2 classes, it's going to be simply Bernoulli distribution, which is here. A point, very important point, is that here I have one yi, I have one xi, or later I use ui, the same. In other words, the information is what? Is kind of a mapping. 1y, 1x. It's point to point. You see it? 1y, 1x, 1y, 1x. But here, it's not. Why? Because have a look at the processes that we used to estimate the parameters. Who cares which yi versus which xi? You know what I mean? I just simply sum all of you up and then make the ratio. That's it. That's why people may feel, hey, is there anything wrong? Because if I have a yi, xi, and yj, xj, here you're not going to see a big difference. For example, y equal to, let's say, -1, y y2 equal to +1 versus y1 equal to +1 and y2 equal to -1. They are the same. Why? Because here I just care, let's say, for example, how many of them are k, and here, oh, okay, here it doesn't matter because here I do have a delta function. Again, delta is the indicator function. I have used it many times in my lecture, so I think you're familiar with my notation here. Okay, so this is a problem. This is somewhat I call it as a group information. It's not completely a one-to-one, point-to-point information. See, but here, yes, it is point-to-point. I have one y, I have one x, and it's, for each one, I have a distribution here. It's really point-to-point. So you may feel, hey, it's something wrong, something unsafe. How can I trust it? That use this kind of group information to estimate the whole thing, and then to train the whole training data, and then make a prediction. No worry. Actually, even if we use the least square, use this kind of point-to-point, point-wise information, it's going to be something very similar. Let's have a look at here. Mahbooba, do you have a question? I saw you raise the hand. Hello, can you hear me? Mahbooba, can you hear me?
Oops. I can hear you.
Looks Arab can hear me as well. Maybe oh, he's reconnecting. Anyway, do you have a question, Mahbooba?
No.
Oh, okay. Just let me know if you have a question. So it doesn't matter here. We can still use a point-wise information, which is what? We simply use the Bayesian. Sorry, we simply use the least square method. We forget about the Bayesian. Okay, there's no Bayesian. We just use least square. That's fine, right? And then I think here's a typo. I'm gonna update it. Actually, use this method. You don't need this assumption. You even don't need the what? Don't need the Gaussian distribution. The assumption here. You can just delete it. I'm gonna update the slides after this lecture, and you will see after some operations, you're gonna see that the optimal solution is still proportional to this. And what is this? Guys, have a look here. Given in 7. Let me go to 7. Oh no, this is logistic regression. Let me find the shadow, the other one. 7 is what? 7 this. See here, this part is this part. And your beta is what? Beta is actually the coefficient of x, right? You're gonna still have this one times inverse of this. See it? Oh, sorry, this one times x. It's proportional. In other words, what? The least square regression coefficient beta is identical to the LDA result coefficient up to a scalar multiplication. That's it. So that you don't need to worry about this. Looks like it's kind of like a group-wise estimation rather than point-wise estimation. The results are the same. The difference is just a scale. That's it. It's just a scalar. That's it. You know what I mean? And we're going to introduce more about this, basically kind of like how to do the regression for an indicator function y in later slides, in later lectures. We're going to introduce, when we introduce actually the regression part. Here, because it's going to involve a lot of calculations, I'm not going to expand it too much. This is just to let you know that using this method for estimation, it's safe. It's going to be similar, or even, I can say, even almost equivalent to the least square method. Okay? Any questions? This is something about the modeling about traditional LDA. Good?
So my question is that in the least square method, so we have 1-by-1 mapping, but in the other one we don't have?
No, you don't have. At least you don't have explicitly. Implicitly, you do have. Why? Because by this delta function, you still have. What I mean is that delta yk times xk, so that you still need to guarantee that this times xi, this xi is indeed under the label of k. Yes. But have a look here. Here, I just care the summation of them. You know what I mean? I don't care really exactly which one is which. Who cares? I just need the summation. But here in the logistic regression, where it is? It's here. Yes, I do care point by point. Why? Because if something is changed, then the whole log function will be very different here. That's why here is kind of like point to point, but here is kind of like a group-wise information. But these operations, this is a small subsection, just tells you that it doesn't matter, because even if you want to run the least square method, which is clearly a point-to-point method, still our coefficients are the same. The difference is only to a scalar multiple, a scalar multiple. That's it.
Okay.
Okay.
Good.
Okay, now the thing is why I call it a traditional LDA, because in many textbooks, they immediately define this one as LDA without any hesitation. The problem is that in some other things, for example, the pattern recognition book, they actually have a more generalized case, which is I name it as generalized LDA. The thing is here, as I mentioned just now, in our traditional LDA, we can actually wrote it in this way, that the W here equal to this part, which is approximately to this, where all this hat means the estimated number, and the W0 equal to this. Let me open the other lecture 7 here. Where's the other lecture 7? Okay, let me show it. No, this is lecture 6. Where's the lecture 7? Lecture 7 here.
Lecture 7 is open at the left side.
Yeah, now both of them are lecture 7. Let me move this one out. The reason I open 2 is because I want to make you, see it more clear rather than just rotate the screen, Here, because online teaching, our vision, the screen is very small, not that big as a whiteboard. So I'm talking about here. So this part is W. Again, I mean, from here to here is W. And this, let me use circle, I think. Oh my God, I really hate to draw it again. This part is W, and this part is W0. See it? That's what I wrote here, okay? WT plus W0. However, an easier way to define, or a more generalized way to define the LDA is by this. I directly define XT to be WT x plus W0. Sorry, yx, not xt. Yx equal to wt times x plus w0. And indeed, as we mentioned in the traditional way, here's the definition. And of course, this is more generalized. Now let's have a look what's going to happen, or what does that really mean if we define in this way. First of all, suppose I have 2 points. Both of them lie on the decision surface or the decision boundary. Then you have what? You're going to have WAXA equal to WXB equal to 0, right? And you substitute to this formulation, you're going to have WT times XA minus XB equal to 0. What does this mean? This means actually here, this is W and this is the decision surface. This means the W vector must be perpendicular or vertical to any of decision point, any points lied on the decision surface. In other words, this W must be what? Perpendicular to this, the whole hyperplane, which is the decision surface, the decision boundary. And the second thing is what? The second thing is that I want to know what is the difference, what is the distance here. This is the origin. Okay, and this is something you can just do some simple operations. For example, here's 2D. I know I can easily calculate A here. This is A coordinate. And then I can calculate the tangent X. X is here. And hence I can calculate the sine X. So this distance equals to this distance, right? And this is nothing but sine X times this length. See it? This equal to sine theta times this length. And by some simple calculations, you're gonna have what? You're gonna have this distance equals to W0, the absolute value of W0 over the norm of W. W0 is a scalar, okay, be careful. W0 is a scalar, and the W and the X, all of them are vectors. And you're gonna see this again in SVM. We use exactly the same way to actually estimate or to calculate the distance between the two hyperplanes, supporting hyperplanes, okay? So the last thing is what? The last thing is what is y rolling mean? Can you show the y? Yes.
I have a question.
Yes.
Where is the W0 on this picture?
Where is W0? No,
Yeah,
there's no W0 explicitly. Why? Because have a look at here. What is this A coordinate? Because how would you draw this red line? The red line is here, right? W1 x1 plus W2 x2 plus W0 equal to 0. See it? So what is the A coordinate? Isn't it very simple? You make a x2 equal to 0. Then you're gonna calculate to get what?
From origin until A, it's W0.
No, it's not. It's not. From origin to A is W0 divided by the norm of W. You know what I mean? Let me ask you this. See my part here, okay? I have W1, what I say? W1 x1 plus W2 x2 plus W0 equal to 0. Now at W2, x2 equal to 0. Now at x2 equal to 0. What is your x1?
X1 is W0 over W1.
Yes, negative. No. Don't forget negative.
Negative, yeah.
Right? You're going to have W0 over W1. Right? And this is your A. See it? And then you can calculate the tangent, because tangent is very simple. This tangent is what? This tangent, everybody knows, okay? It's nothing but a negative W1 over W2, right? You just, make this one to the right side and W1 over W2, right? So that your sine is what? Your sine theta equal to this, negative W1 over W2 norm. Now you have this A distance. You have sine theta. Can you calculate this distance? And until just the length, the distance of this A times sine theta. And then here you go. Don't forget absolute value, because I'm talking about the distance, not this coordinate distance, so that you need a absolute value here. Actually, in the textbook pattern recognition, the author made a mistake here. The author directly put a negative W, which is wrong. Why? Because we're talking about distance. We're not talking about the coordinate or displacement. Okay, we're talking about the distance. Anyway, so in this case, I have this. The final thing is I want to know how far is here. So to get this length, I name it as R. We have a very simple method, which is here. Let me open the other 7 so that you can see it easily. The picture is here, okay? To calculate this R, what I'm gonna do is this. First of all, I make this is a projection point, the projection of X onto this decision surface, okay? So I have X, I don't know how to read this, X perpendicular, let's say, call it X perp. So that if I have the X perp here, I have X equal to X perp plus this vector, right? From X perp to X. I have this X, the vector X equal to this vector plus this vector. Let me draw it. How to draw this vector plus this vector, right? Okay, so this vector is the X perp, I already have it. So this vector is what? This vector, the direction, I know. Why? The direction is exactly W. See it? Now I make the unit direction of W, which is this part, which is W over W norm. So this means the unit vector, which is this direction. Now R indicates how long this one is. So that I must have X equals to X perp plus R times this unit direction vector. And I'm gonna multiply both sides by WT and plus a W0. You're gonna have this one, right? And you see what? This by definition is what? This by definition is my y-axis, right? Because my y-axis is defined in this way. See here? My y-axis is defined in this way, okay? And let's move back to the, oops. And this part, look at here. This is 0. Why? Because X perp is perpendicular to W. See here? And sorry, not this part 0, my fault. This part plus this is 0. Why? Because x perp is on the decision surface, so that I must have x wt times x perp plus w0 equal to 0. So finally, you have yx equal to this part, and simply you get the length formulation is this way, and hence you have this picture. So this is a graphical interpretation of the y. Actually, y is nothing but this distance. Sorry, but this actually I should say this vector over W2. Another thing is I think I should not claim R as a length. It's something like a displacement. Why? Because R could be negative. Why? Because here we need to code the YXA. Usually, for example, suppose I have 2 classes. What I'm gonna do is that, for example, I can code here. I can code, for example, y equal to -1 if it's class 1, and y equal to +1 if it's class 2, right? We can do it in this way. So the y could be negative. In other words, this R could be negative. The norm is always positive, you know. Okay, so in other words, for example, your x could be here. We can have a point here. Then your R is gonna be negative distance, like here. So if my x is in this direction, I must have y greater than equal to greater than 0, and we're gonna name it to be class 2. And if y is this direction, we have y less than 0, so it's gonna be class 1. Okay, and of course this is decision boundary or decision surface that y equal to 0. If it exactly sit here, then whatever, you can predict whatever class. But in the practical case, that it exactly lies on this decision surface, the probability is almost 0. It's almost impossible. So you don't really need to worry about this point. Okay, any questions here about this geometric interpretation? No? Good. Okay, now let's continue. Oh, let me erase this box, clear all drawing. Okay, let me use this one. I think this one's easier. Now the question is, how would you make your decision? Suppose we have 2 classes. Let's say suppose we have m classes. We're going to do exactly the same. So suppose suppose I already have the W. I already also have the WK0. And for each, sorry, I should say this, sorry. If I have m classes instead of 2 classes, this model is just for 2 classes. This model is for 2 classes. For a 2-class classification problem, we have this. What if we have, let's say, m classes? What we're gonna do is that for each class, we're gonna create a YKX and equal to WKTX plus WK0. And then if suppose we have already trained our WK and the WK0, for a target data X, we're gonna predict it to class K if YKX is the biggest one. Okay, so this is exactly the same as what we did in what? In the traditional LDA. Remember traditional LDA, what we did? We used this 4, see it? And this 4 is equivalent to what? I really hate the screen here. This 4 is equivalent to this. I'm gonna predict the biggest probability. While in the generalized case, what we're gonna do is that we're not gonna use the probability, or we're not gonna simply use the probability. Instead, we're gonna use a label function, which is YK. This is more in the sense of regression, you know what I mean? And we're gonna take the biggest YK. The YK here works something like a linear discriminant function. Looks like this CK. Where's the CK? Or the original meaning as what? The probability. Which one is the biggest? And then I'm gonna predict it to that label. That is the meaning, okay? So this is something as a very, very simple introduction about the generalized LDA. In the following, we're gonna go back to the traditional LDA, okay? Without otherwise mentioned, we're gonna assume that all the LDAs that are mentioned in the following are traditional LDAs, okay? The meaning, the purpose that I added this LDA is to let you know that in some cases, we do not have to set up everything, the 2 assumptions for the LDA. And somewhat you know, the assumptions, or let's say the definitions in many textbooks about LDA is kind of like a bit narrow. You know, we do have some generalized cases here. Okay, another thing I want to introduce is the QDA. Of course, we're talking about the traditional QDA. The QDA, actually, the motivation is from here. In the classical, in the traditional LDA, what we assumed? We assumed two things. First, the X is normally distributed, given class K, right? And the second thing is that it's here. And the second thing is that all sigma Ks are the same, meaning that all different classes of the data share the same variable. Share the same variance. The question is, well, this assumption is still not that bad because, you know, due to the CLT, the central limit theorem, we know that if we have huge amounts of data, whatever, it's going to be normal. But this assumption is very strong that every class of the data must have the same covariance. Then we're asking, what if we drop this assumption? We only have this normal distribution assumption. What's going to happen? And this finally leads to QDA, quadratic discriminant analysis. So to answer this question, we have to recalculate 3, this log ratio. And this step is still the same. And then you're going to have this. Why? Because here, let me go back to 3 and quit this mode. I don't know whether I can use a word to write this. It's going to be really long, I'm afraid. I wish I had a whiteboard, which makes my life much easier. Have a look here. Here, you no longer have this equation. Why? Because I have a K, sigma K here, and I have a sigma L here. You know what I mean? So that I cannot combine using this 3C. Instead, I have to brutally calculate it, which is here. Let me see, how can I show you this result? Which is here, sorry. Another thing I forgot to mention is this. We do need a delta function here. Where are they from? Let me see here. It is simply from the function, it's simply from the f function here. Think about this. Suppose I have, it may take a long time, however. Suppose I have log of, let's say, fk over fl, okay? And what is that? Don't forget that we have this item now, because previously all sigmas are the same. So for fk and fl, this item is canceled. This delta square of the determinant sigma. But here we do have this. What you're going to have is that you're going to cancel this part, but here you will have what? You're going to have -1/2 of, let me see, how can I bracket? Half a log of dt sigma minus log of dt sigma L. That's something that you cannot, omit it anymore. Why? Because you do have this item. And the second item that is the same here. You're going to do nothing but just expand it. And after expansion, by the way, do you get my point? Because here it's not convenient for me to write down everything step by step, so that I just indicate it in this way. Just to let you know that this one is from here, okay? This one from here, basically from the PDF, which is a denominator of the square root of the determinant of log, determinant of the sigma K matrix. And this part is copy and paste, the second part. Now the question is what? The question is, if you expand it and simplify it, you're going to get this formulation. Why? Because again, I apply the idea of the linear discriminant function. Here I have the quadratic discriminant function, so that I take this one out. Let me erase all drawing, and then let me take a new one. I take this one out. and take this one out. And I'll take a log pi out. So that I have this. After simplification, you can simply define the quadratic discriminant function in this way. Why it's quadratic? Because I have this item. This item is clearly quadratic item. See it? With respect to x, okay? Because x is here, the data. Get a point? So that we're going to do exactly the same. How do we make the label prediction? We're going to calculate all the sigma k's and see which one is the biggest one. The one biggest, we are going to predict the target data to this label k. That's it. Okay, so here I wrote the parameter estimate. First of all, parameter estimations are exactly the same as what we did here. Let me clear again. As we did here. Parameter estimations are the same here. But be careful that I no longer have a common sigma. Instead, I'm gonna have what? I'm gonna have a sigma for each here. I'm gonna have a sigma for each of them, for each class, which is here. Compare this one, 6C, with the 12. What do you see? Here, I have a summation for all classes here, but here it's an estimation for sigma k that I don't have a summation for all classes. And another thing is that here I do have n minus 1 instead of n minus m. Because why? Because here for each class, I'm gonna do it this way, okay? So this is the only difference in terms of the parameter estimations of the Gaussian distribution. The second thing is what? The second thing is how would you determine the label? And this is exactly the same here. The label prediction is also the same as LDA by 4, in which this c becomes here, the quadratic discrimination, the discriminant function defined in 11 instead of defined in 5. This 5 is a linear one, and this 11 is a quadratic one. Since it's quadratic, we call it quadratic discriminant analysis. Okay, so everything, okay, everything simple. Now I do have a example here. Let me use part. The example is, why so stupid? I cannot directly, let me see. And how about I do it this way? Zoom full screen. Now can I do it? Still the same. Habuba, do you know the solution? You know what I mean? I want to just simply rotate it. I mean, directly roll it down rather than just, you know what I mean? Like
I don't know.
By page. And also it's in the Zoom. Anyway, I think we're gonna be adapted to it after several lectures. It's also very new for me, this kind of online education. Okay, the examples are here. So this is a LDA result. This is the data, 1, 2, 3. And you can see we do have a lot of mispredictions here, okay? And the second data, okay, let me put the second data here. As here. This is the QDA result. They're exactly the same data, okay? Let me make it bigger here. And you can see QDA is clearly better because, you know, quadratic gives you some curves here. Compare this one with this one. Clearly, this one's better, right? Okay. Now the thing is that we're smart. We're gonna have a trick. So here, we have 2 dimensions of the x. And I'm gonna refine it, and I'm gonna recode it to be a refined LDA with 5 dimensions. How do I get the 5 dimensions? I make it in this way. The first 2 dimensions are still x1, x2, the original data. The third dimension, I make it to be x1 times x2. The fourth is x1 squared, and the fifth is x2 squared. So in other words, I'm gonna run the LDA in this 5D feature space, rather than the traditional or the original 2D feature space. Get a point? And here you can see, it's a huge improvement here. See it? From this original LDA to this refined LDA, in which I have 5 spaces, 5 feature spaces. Actually, this is refined or recoded. And if you compare this one with this one, actually it's difficult to tell which one is better, to be honest. Because this one is better in this region, but it's worse in this area. But the QDA is, you know, the opposite. And you may say, hey, this is just for this example, is it in general? Well, in many cases, yes. The QDA versus this kind of recoded or refined LDA, the difference is relatively small. Do you know why? One very important reason is why I recode the LDA in this way. Somewhat is because I want to use these quadratic items to something like make it LDA, something very close to the QDA. You see what I mean? I actually recode it in this way on purpose to make it close to the QDA. And finally, of course, these two results are relatively close. And this recoding method or refined LDA method is commonly used in practice because in many cases, if you just have a simple linear, discriminant analysis, as we mentioned, the decision boundary is going to be what? Hyperplanes, or let's say they are linear. It's not that good, or it doesn't really work in many cases. For example, something like this, because data, your practical data are not that perfect, trust me. However, if you use quadratic, then you're going to have some curvature. Then the application area will be much, much bigger, and it's going to be better. And in real applications, usually they are going to apply both recoded LDA and QDA. And to see which one is better, then they're going to keep that one. That's the point. Okay. Any questions here about this example?
I have a question.
Mm-hmm.
So when we refine the linear discriminant analysis, LDA,
mm-hmm.
like the picture that we have here, yeah, exactly.
Yes.
So it's for a very simple case that we have 2 dimensions, x1 and x2.
Mm-hmm. Yes.
So if we have
3 dimensions, what you do, right?
If we have a lot of dimensions, it's not going to be as easy as this.
You nailed it. This is absolutely correct. This is absolutely correct. And for example, suppose we have 3 dimensions. How many items would you have? You're going to have x1, x2, x3, x1, 2, x1, 3, x2, 3, and then x1 square, x2 square, x3 square. You're going to have 9 items. See it?
9 items.
Yeah, it's going to really be a lot, right? Not to mention that if you have, let's say, d dimensions. Yes, the truth is that, yes, it's going to be a lot. And that's something I think I'm going to add something after today's class because I think it's still important. I may add one more section here to be a reduced rank section. So another point is that we are going to somewhat want to kind of like reduce the dimension space. So that here, for example, if we have d-dimensional spaces, we're going to see whether we can make it kind of like smaller. This is something like the Fisher discriminant analysis.
Okay.
And we're going to introduce a little bit later, but you're absolutely correct. In general, when our dimensions are bigger and bigger, this method will not be that convenient. You're correct. So we may use some other, let's say even some PCA, principal component analysis, to do some dimensional reduction. But PCA is very different from here, if we are considering the reduced rank LDA, because here we're doing classification, but PCA is not classification, it's unsupervised learning. Somewhat like, no, I cannot say it's clustering, but it's somewhat like clustering because we don't have a label given label anymore. It's unsupervised. Okay.
Okay.
So then a problem is how to directly calculate the LDA. People say, hey, it's really simple. See, here I have already, let me make it bigger. Let me directly use this screen. For the LDA, I have already defined the linear discriminant function here, which is this one, right? And as we know, we're going to calculate this one for each k, and we get a maximum done. For the QDA, similar, we're going to do, where's my QDA quadratic function here? Equation 11. We're going to just, okay, calculate this one, and then find the maximum, and done, right? So why it's complicated? Because if you carefully have a look, you have this item, inverse matrix, see it? And also you have this item. This is simple. This is because, no, this is not simple because here your sigma k is still a dense matrix. It's a covariance matrix. It's a dense matrix. To get a determinant, it's not that easy. And the same for our linear function here. Where's my linear quadratic? Sorry, my linear discriminant function. I cannot find it. It's here. I have an inverse. The good point is that here I don't have a log determinant because they canceled. Then how to handle it? You definitely don't want to brutally calculate the determinant and get a log. And also you don't want to brutally calculate this inverse matrix. As you mentioned, as Said just mentioned, if my dimension is very large, it's gonna kill me, right? It's gonna be very, very terrible because this sigma, the dimension d by d. D means the number of feature of the x. Okay, one method we can use, a very simple method, is the eigenvalue decomposition. I think eigenvalue decomposition, everybody has heard before, right? Not singular value decomposition. Singular value decomposition is maybe a little bit new to some of you, but eigenvalue decomposition is really, really simple, taught in undergrad level. So I have this. By eigenvalue decomposition, this V is the eigenvector space, and this D is what? As a diagonal matrix composed of the lambdas. Lambda means the positive eigen values. You know what I mean? I'm gonna have a matrix like this way. Like what? V times how to draw matrix here in the Word. I wish I can use the latex, which is easier. Let me draw. Let me see here. I think. Okay, and then I'll make a matrix.
You can open and text, and
I know, but it's not that, because not every one of you use the text, and also I'm gonna upload it online. You know what I mean?
Oh yeah.
So it's gonna be d dots. I'm already using the text language to write it. You can see lambda d. Okay, assume it's a full rank. Of course, it must be full rank. Otherwise, something's gonna be wrong. Okay. So what I'm talking about is it's going to be like this way. And this, I need to have another D, another V. And this is your D matrix. Or I should say, let me give it a K here, a DK matrix, okay? Lambda, let's see, how do I code it? KL, okay. So it's K1, and this is KD. And this is also a VD, VK. Okay, so this is the decomposition. And by basic linear algebra knowledge, you know that this V matrix, which is what? Which is for all the eigenvectors, they must be what? They must be orthonormal. Okay, this is the definition of the eigenvalue decomposition. Question: is it guaranteed that I must have it? Why? Because be careful, eigenvalue decomposition, as you cannot claim that eigenvalue decomposition exists for any matrix, or even any squared matrix. No. Singular value decomposition, yes, exists. Singular value decomposition is nothing but you change this V to be U. Eigenvalue decomposition is a special case of the singular value decomposition in which the U equals to V. Okay, and this matrix, this kind of orthonormal matrix, we also call it a unitary matrix. Why? Because for orthonormal matrix, you have a very, very, very special property. Orthonormal matrix or unitary matrix. The property is that VT equal to V inverse. This is a super, super important thing. Why this holds, Mahbuba? What's the meaning of ortho, let's say ORTHO? Actually, orthonormal means orthogonal and normal, right? So this ortho means orthogonal. Orthogonal means what? Suppose I have a V equals to, let's say V1, C dots, VK, VD, all of them are vectors, okay? So let me bold it. I wish I can use BM, which is gonna be much, much easier and faster. Orthogonal means any vi vj equal to 0, right? This is orthogonal.
Right.
Okay, and the normal means what? This is, let me see, this is orthogonal. Orthogonal. And normal means the norm of any vi equal to 1. That's the meaning of norm, right? And as long as you have this, it's very easy to see that Vt must equal to the V inverse. Okay, this technique is commonly used for this kind of matrix. Then let's go back to the question. How do we know that this one must exist? The reason is because this is a covariance matrix. Covariance matrix has a what property? It must be positive semi-definite, right? Then, of course, if a matrix is a positive semi-definite, you have what? You have all eigenvectors, sorry, you have all eigenvalues must be positive, right? And hence, as long as all eigenvalues are positive, then this matrix must be a full rank matrix. In other words, you must have it. Get a point here? That's why we don't worry, hey, what if, let's say, the eigenvalue decomposition does not exist for the sigma k here? No way, it must exist, okay? So after this, you just get the inverse of this one. Inverse of this one equal to this. Very simple, right? Why? Again, inverse of this one. Okay, let me write a little bit down.
I have one question.
Yes.
Yeah, here sigma is positive semi-definite or positive definite? Is positive semi-definite?
Sorry, definite, my fault. Positive definite, not positive semi-definite. Positive definite.
But
I said a
sigma...
positive semi-definite, right? My fault. It should be PD, not PSD. Okay.
Okay. Thank you.
Yes, you're welcome. Inverse, this equal to what? This equal to the inverse. Let me directly use sigma and the VD, okay? I'm not gonna put the K to save some time. VD, VT, inverse, right? And this equal to what? This equal to VT,
T
of
inverse
the inverse and D inverse D. What happened? Oh my God, I cannot tolerate my laptop. The keyboards are really, really small. And V inverse, right? And then how to do, guys? Simple. Inverse equal to T. So this one equals to what? This one equal to V itself. And this is D inverse. And this one is what? V inverse equal to VT. And that's how you get this formula, okay? So what's the point? The point is that my D is what? A diagonal matrix. If this diagonal matrix, so D inverse equal to what? Isn't it simple? My D inverse simply equals to this, right? D inverse equals to the inverse of everything here.
Yep.
So ugly. Anyway. Okay. Then everything is going to be very, very simple. For example, in 4, let me find another one. In the linear discriminant function, the definition 5 here, I need to calculate this item, right? And also this item. Okay, now I have what? I have this item, you just plug in. You're gonna have this item equal to this. And anyway, this is the example before. And this item here equal to what? This item here, you just plug in and equal to this. Why? Because this is you just plugging, plugging the inverse. And then you're gonna make this part together. Let me make a draw here. You're gonna put this part together. Okay, this equals to this, very clear. And you're gonna keep this one here. This equal to this. See it? So what's the point I draw, we write it in this way? The reason because these two are identical. So that you can, sorry. Let me, can I erase this part? Erase this box. Okay, yeah, good. Then I can make here I should include this V. No, I should not. I don't need to include this V. Give me 1 second. Well, do I make a mistake? I think I have a typo here. Did you find a typo here? Delete this V. This V is wrong. Oh my God. Why cannot erase it? Oh no, I really messed up the whiteboard. It's so slow here. This equal to this. In other words, let me see, how can I change the color? Okay, let me show you the screen. I'm doing here now. What is the color? Let me choose a white color, and then let me choose this one. In other words, this V is, can I delete it? Yes. In other words, this V is something additional. I will update it and delete this VK. Okay, here's a typo. And so actually, we directly have this equal to this, right? And in some cases, you can further decompose it in this way. Clear all drawings, and oh my goodness, I have to choose back. Every time I have to switch. You can further decompose it in this way, that it equals to x minus mu t, and here is sigma inverse x minus mu. This equal to blah 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 equals to vt x minus mu this t, and d inverse times this. This time I'm smarter. I know how to copy and paste. This is, you know, this v again is redundant. Then I should have this, right? And here you can further decompose it in this way. Put an half here. Oops. Okay, and then you copy and paste. See it? So the difference that I decompose this D inverse to be half a half. Then you're gonna ask, so what's the point? The point is that you can write it in this way actually, which will greatly simplify your life. It's equal to, let's say, BT times B. Done. Get a point? So in this way, it's going to be very, very fast to calculate this. And there are some iterative method using this idea. And the last thing, to get the quadratic one, the quadratic discriminant analysis is here. You need a log determinant. Okay. Now, how to do the log determinant? We're going to do it in this way. First of all, the determinant of sigma det of, let's say, ABC equals to det A times det B times det C. This is very simple. Everybody knows, right? Okay. So sigma equal to what? Sigma equal to VK D and VKT, right? So it's simply equal to this. And of course, determinant of VK equal to the determinant of VKT, the same, okay? And since what? V is what? Orthonormal matrix, the determinant of that equal to what? Equal to 1, okay? So it is, give me 1 second. Yes, I can claim it. So this item is gone. This item is gone. And finally, I only have this item. See point here? So that I directly have this one equal to log determinant of delta of dk. So what's the point? The point is that dk is what? A diagonal matrix. For a diagonal matrix, something like, for example, something like this way, d equal to this. How would you calculate its determinant?
multiplication of the
Yes,
diagonal.
absolutely. Yes. It's very, very simple, right?
Yep.
The log of determinant of this one. This equal to what? This equal to log of what?
Pi.
Pi PROD. Let's say J of nabla Kj, right?
Sure.
And this finally equal to what? Nothing but the sum of J of the log nabla Kj. And that's how, here, why use the D here? It should be nabla, not a D. Here, this D should be a nabla because we define, let me see, what is my notation? Yes, my notation is nabla here. So this should be a nabla D here. So in this way, that's everything. Because using this way, you can what? You can simplify this 11, which is a quadratic discriminant function. And you can also simplify 5, which is the linear discriminant function. And here you go. You know what I mean? So all the calculations can be done more efficiently, much more efficient or much faster than you brutally calculate the inverse matrix if the dimensions are big, or you brutally calculate the determinant of this. Okay, any questions? I think that's all of today's class.
Okay.
Yeah.
It's actually longer than my expectation. Indeed, I mean, let me go back. Now you can see me.
Yeah.
Indeed, the online class, I mean, I haven't been very adapted to it. If you're interested, you can play with it. You can play, can you see my screen now? Can you see my screen? Yes. Yep. You can play with this, you know, all this kind of thing. Every time you have to erase, and every time you, after erasing, you to put it back. Oh my God, so slow it is. And also it's very slow to write a formulation here. Arab, if you don't mind, next time I may try text. Directly write the latex if you don't mind. Latex is a bit faster than than this. But to be honest, I don't feel it's gonna be much faster. You know why, Said? Because if we are writing some difficult formulations, you still have to see step by step, like copy and paste. You know what I mean? Something very similar actually. One reason it's kind of slow is because I'm using my laptop to type. The keyboard is not that good, especially typing the numbers. It's very, very small. It's not like Office, you know, desktop keyboard. That's really easy. Anyway, I will try to improve it with more and more lectures. And thank you very much for this very first lecture. Stay safe and see you on Wednesday.
Yuan, I have a suggestion. I think there is a software or something like, for example, the Note. Then you can write down by the mouse on it. Yes, you're absolutely correct. And Zoom itself provided. The question is, you don't want to use the mouse to write a formula. Trust me, Said. If you don't believe it, you can try to write an integral to see what does it look like. So it's very bad. Very, very bad, not very bad even. That's the first thing that I tried. When you share the Zoom, you're gonna see the whiteboard. There's a whiteboard there so that you can draw the thing, whatever you like. Use your mouse, right? I cannot recognize what I was writing, so I immediately give it up. Oh, okay. Yeah. I haven't tried that. I just. You can play it after this class to see whether you can write the formula. Not to mention this kind of difficult formula, even some super simple formula. Let's say x equal to AB, to see whether you can recognize by yourself. Okay. Okay. Anyway, we can discuss it a bit later, and see you on Wednesday. Goodbye, guys. Stay safe.
Okay. Goodbye.
Bye.
You.
Yeah.
Bye.
Bye.